Prem sir? Prem sir?
Good afternoon, ma'am. Good afternoon, ma'am.
Sir, shall we start or wait for 2 minutes, sir?
Ma'am, ma'am has joined, ma'am. Yeah. Yeah, ma'am has joined, ma'am. Ma'am has joined.
Yes, sir. Yes, sir.
Dr. Ramaprabha, ma'am has joined. Ma'am, we'll wait for 2 minutes, ma'am.
Okay, sir. Okay, sir.
Okay, ma'am. Thank you.
Okay, sir. Thank you.
Selvarani ma'am, you can start.
Sir, wait.
Sir, 1 second, sir. Arun, sir. Selvarani, ma'am, 1 second.
Okay.
Please, actually, ma'am, voice problem இருக்கு. So 1 minute, 1 second, please.
Okay, sir.
1 second, please.
இல்ல டெஸ்டிங் செக் பண்ணிக்கோங்க சார். ஸ்கிரீன் ஷேர் ஆகுதா இதை செக் பண்ணிக்கோங்க.
சார் வந்து ஆக்சுவலா மேம்க்கு வந்து வாய்ஸ் வந்து இது ஆகல, இங்க ரீச் ஆகல, ஸ்பீக் பேசுறது கேட்கல. 1 செகண்ட், அதான் பேசிட்டு இருக்கேன் சார் மேமோட. 1 செகண்ட் சார்.
ஓகே, ஃபைன்.
மேம், செல்வராணி மேம்.
Okay, sir. Okay, sir.
மேம் வந்து திருப்பி லாக் அவுட் பண்ணிட்டு ஃபுல்லா வராங்க மேம். ஆக்சுவலா வாய்ஸ் வந்து மேம் வாய்ஸ் ரீச் ஆகல, பட்
சரிங்க சார்.
அவங்க பேசுற நம்மளுக்கு ஓகே மேம். ஓகே மேம்.
சொல்லலாமா?
Can you hear me, sir?
Yes, ma'am. Yes, ma'am.
Then
Okay.
Ma'am, please increase your volume number, ma'am.
volume number.
Volume.
Okay, sir. I'll see, sir. I'll see it.
Okay, volume number only, ma'am. Now your voice is audible, ma'am.
Yeah, it's a high only, sir. Now it is okay, sir?
Now it is okay, ma'am. Now it is okay, ma'am.
Okay, it is closer to me. The mic is closer to me now. Okay, sir. It's okay,
okay,
now, sir,
ma'am.
now?
Thank you, ma'am.
Now
Thank you,
okay,
ma'am.
okay, okay.
Okay, ma'am. It's okay, ma'am. Okay, ma'am.
Okay.
Ma'am, please share your screen, ma'am. 1 second, ma'am.
Okay,
Please share your screen. 1 second, ma'am, so that we can see the screen sharing.
Yeah, is it okay, sir? Is it?
No, ma'am. Screen is not yet shared, ma'am. You have to pin the screen, ma'am. You have to pin your screen, actually.
Okay, fine, sir.
Still now, you have to give present now.
Yeah.
Like
That only I'm going, sir. Wait, 1 second, sir. I'll again give, sir. Yeah. Now it is showing, no, sir?
No, ma'am. 1 second, ma'am.
Yes, sir. Now it is. I
Second,
think it's,
yes, ma'am. Yes, ma'am. Your screen is visible, ma'am. Your screen is visible,
okay, sir.
actually. Okay, ma'am. Thank you, ma'am. Thank you, ma'am.
Okay, sir. Is it visible? No.
So 1 second.
It is clear.
Yes,
no,
ma'am.
sir?
Yes, ma'am.
The voice
Visible,
is
ma'am.
clear?
Yes, ma'am.
Audible.
Clear voice is clear.
Is that audible?
Screen is visible, ma'am. Audible, ma'am. Audible, ma'am.
Okay, sir. Okay.
Ma'am, shall we start, ma'am?
Yeah, sir. Yes, sir.
Okay, ma'am. Okay, ma'am.
Thank you, sir.
Silverani, ma'am, can you start the session, ma'am, please, ma'am?
Priya? Okay, Priyadashini?
Silverani.
Wait.
Okay.
Huh? Okay, you can start first. Okay.
Greetings to one and all present here. Myself G. Priyadashini and Prajna Agnes Rebecca of 3rd year EC Department, Panimalar Institute of Technology, the host of today's presentation. On behalf of Department of EC, Panimalar Institute of Technology, Chennai, Tamil Nadu, in association with IEEE EMS Madras Chapter, PIT EDC, IIC, IEEE Students Branch, IET ISF. It's my immense pleasure to welcome you all to this AICTE sponsored short-term training program on mission vision for entrepreneurs learning startup with low seed fund.
Priyadashini, your audio is muted. Priyadashini, you can unmute your audio and proceed.
Sir, Rajini will be speaking the welcome speech, sir.
Okay, ma'am.
I'm honored to welcome Dr. P.S. Ramaprabha, Professor and Head of the Department of Electrical and Electronics Engineering, who has a teaching experience of 20 years with 12 years of research experience. Her research interests in image processing, medical imaging, embedded, Internet of Things, and renewable energy. She has graduated from SRM Ishwari Engineering College, Madras University, Chennai, in Electrical and Electronics Engineering in the year 2000. She has obtained her Master's in Satyabama University in the year 2006 and PhD degree also in Satyabama University, Chennai. She has started her education career in the year 2000 as a lecturer. She has accomplished a groundbreaking research on the early diagnosis of cervical cancer using colposcopic images. This astute research has brought her the pride of earning doctorate in engineering and biotechnology. She has jubilantly participated in numerous national and international conferences conducted by reputed organizations. She has published several papers in international and national, and also presented 20 papers in the International Conference and National Conference. She is the member of IEEE, Life Member of ISTE, IETE, and IEI. She has received Outstanding Women and Young Women Scientist Awards. It's my honor to welcome you, ma'am. Welcome, ma'am.
Thank you, ma'am.
I would like to welcome all the participants who are present here.
Now, without any further delay, we'll turn the time over to our presenter. Ma'am, please.
Thank you for your introduction. Once again, I'll thank all the coordinators of the Panimalar Institute of Technology ECE department for conducting this AICT sponsored STTP on mission vision for entrepreneurs launching startups with low seed funds. Yeah, and there's no introduction there. I think there's no need of introduction about me because Priyadashni, I think Priyadashni and other student have introduced me very well. Thank you. And once again, a very warm good afternoon to one and all gathered for this STTP. We'll move on to the session. Now, today we are going to see about the medical imaging, which is disease identification, implementation aspects and procedures. Actually, for the entrepreneurship, we are dealing with the entrepreneurship. Actually, medical imaging and diagnosing is a very high and innovative life science segment. Compared to other segments, the medical imaging is very easier. That is, there is no that much cost is required. That is what is today's topic. For the entrepreneur to become an entrepreneur, we have to invest our ideas and our talents. We have to invest, and with that we can make in terms of the entrepreneur. So nowadays, erosion of turf is very gynecologist, whatever it may be, it is very tough to identify the uh, true values. For that only we are need of the disease identification. For that we are dealing with image processing. The content what we are going to deal is the introduction, image enhancement, techniques, and the image enhancement techniques, and color image enhancement, and finally conclusions with the reference we are going to see. Mainly when you're going for the image processing, we have three classifications. One is the restoration, second one is the enhancement, and third one is the extractions. These are the three main parts of your image diagnosing. When you are diagnosing any part, without this we can't able to diagnose. So that this is the main three classifications of the image processing. And first, today we are going to deal with the image enhancement. So actually, enhancement means which is going to improve the quality of the image of the human perceptions. So we are going to improve the quality, further a processing of the images, like to identify the cancer or whatever it may be. We have to enhance the image. And even nowadays what we are doing it, if we are in our mobile also, if you want to see the clear picture, what we are doing it, we are uh, scrolling, and we are taking enlarging our image now, so that before going any process or anything, we have to enhance, we have to make the pixels and everything in terms of the clear image. And then after that only we have to identify what is the problem, what is the problem in that particular image or a particular part. We are going to see that only. Okay. Now, in a image enhancements, we have two main parts. One is the first one is a spatial domain, and second one is a frequency domain. See, actually, what is a spatial domain in the sense? The We have to work on the image plane itself. That is, directly we have to work with the pixels in an image. That is the spatial domain. But in a frequency domain, we have to take the Fourier transform coefficients of an image, and that with that we have to process, and we have to take the inverse Fourier transform and to modify the things to get the enhancement image. Say, I'll be moving on to the basic of the image processing, because for the entrepreneur, they should know the basics. Then only they can improve the quality, and they can diagnose the diseases. So next is I'm moving on to the spatial domain. In the spatial domain, we have 3 points. One is a point processing, another one is a histogram processing, and third one is a mask processing. First, for this any spatial domain, I already told you, which is going to take in terms of the pixels. So g of x comma y, that is, image will be in terms of the f of x comma y, has to be transformed into the g of x comma y. That transformation we are going to take it over here. And all this what we are going to deal is a spatial domain. So everything which will be in a plane which is going to take in terms of the pixels. So if I'm taking into a particular part of the x comma y, this is a plane. In that, this is a, for example, we can take into a 3 cross 3 pixel, and this is a x comma y of the pixel. In that pixel, we have to change whatever the modifications we wanted to change, we have to take it in that. and that in a point processing, the transformation has to be taken into from the darker to light, and that is darker to light. We have to from 0 to r, and that will be transformed into s is equal to the transformation of r will be taken over here. Okay, and next part will be the mask processing, that is mask operation. Whatever be the mask will be prepared, and that mask will be embossed into this in pixels. So that weightage will be added with this original pixels, and that will give the enhanced results. That is, yeah, we can see this equation, g of x comma y is equal to summation I is equal to -1 to 1 and -1 to 1, and which is x comma y, that will be weighted. This weighted, actually the mask will be embossed into the original image. That weighted will be multiplied with the pixels of the each and every original image. That is, your f of x comma y is the original image. That pixels of the x plus y and y plus j will be the images character. I is equal to -1 to 1. No, that is what here this will be multiplied with the weighted value with the original image, and which will enhance the image. This is the mask processing, mask operations. The previously what we have seen is a point processing, which will be point by point, which is going to raise the intensity. When we are going for this narrow point, that is the narrow straight line, and again it is which is coming under the threshold value. This is either the 0 or the 1 value, that is negative value, or else a black and white value, that we can say in terms of the negative image like that. But here we will be just going in terms of the gray to the dark value, white value. Okay, next is yeah, this is digital negative. I told you, the point processing will, which is going to give in terms of the negative image, and which is going to transfer in terms of the L minus 1 minus R. That means which is ranges from 0 to L minus 1, again 0 to L minus 1, which is going to give in terms of the negative value. The image, this is the image with that we are going to get it in terms of the negative image. So this part will be the, with this point processing we are going to, this is the affected area, this is the mammogram image, and this is the input image. If you are giving the point processing, we'll be getting the negative. So what is that point of giving this negative means? This part sometimes, which is maybe in terms of the nerves or whatever it may be, but we are going to identify the lesion part. This is actually a cancerous part, so which is going to identify by using the a negative image. And next, when you are going for the logarithmic transformation, and this is also which is going to give the clear picture of, this is the original image of the x-ray, and when you are applying the logarithmic morphologic of this particular image, we can see the cracks and all, and we can see this here, we can see this x-ray image clearly with this logarithmic transformation. So in x-ray image we can able to see the correct clear picture of this parts, bones and all, we can able to see that great, so that we can so why I'm telling means we can even see this, we can diagnose that even in ordinary x-ray. This is x-ray inputs, but in this x-ray inputs the doctors are fail to capture the disease, or sometimes they may uh, they are all the human being only, so human perception may vary. So person to person the perception may vary. So even when we are making in terms of the machine, what will happen, it will be trained, we are going to train the system. So what will happen automatically, which is going to give that, in our system we have trained and we are feeding that input. What will happen, we are going to get that disease correctly, accurately, which is going to give uh, false negative and false positive, everything, which is going to, we are going to give the hundred samples to the system, and we are going to train our system. So nowadays we have artificial intelligence also for that. So when we are training that, what will happen, we'll be getting the accurate result. So once the accurate result gets, the patients can be cured easily. So that's what we are going for this image processing also. Yeah, in this For example, original digital image, X-ray image, we cannot able to see this particular parts clearly, correct? So, but when you are giving the after this image, when you are taking into your image processing and we are applying the logarithmic transformation, we can able to see the clear picture. So, and here also see the X-ray image of the lung, and but here we can able to see that clearly. So, when you are applying the this spatial domain itself, this is a simple domain. Even this simple domain, we can able to get the accurate result in a diagnosing the images, medical images. So the doctors can be easily identify, or which is mainly used for the radiologist for the easier and faster communicating the diseases. Otherwise what the doctor will be doing, or otherwise what we are doing it, we are going for the second opinion and third opinion, correct? So instead of that, when we are going for this techniques, we can easily identify this is what is the problem with the patient, and we can diagnose earlier. Even in a cancer and all, when we are diagnosing earlier, which will be earlier diagnosis will be early cure. So that we have to go for the image processing. Okay, next is the what is the advantages of the logarithmic transformer? That what logarithmic morphological transform presents above the are useful to any medical applications with the automatic contrast enhancement or sharpening is needed. And sometimes all these things are needed. We are dealing with the X-ray images, is it? So there we need as a contrast enhancement and sharpening is needed. So that we are going for the logarithmic transformation, which will be mainly used for the digital X-ray, digital mammography, and CT images, nuclear magnetic NMRI, and sometimes we'll be taking this into a telemedicine applications also. Okay, and this logarithmic transformation, the most important performance of this logarithmic morphological model are, which is sharpening. That is a compensation of a blurring introduced into the image by image formation process. This allows fine details to be seen more easily than before. That's what I told you. We can, when you are going for the sharpening the images, we can go for the logarithmic transformation, and which is able to increase the large dynamic range. Okay, and contract color constancy also, which is removed, and it is ability to remove the effects of the illumination from the subjects. This allows consistency of the output as illumination changes. And next method is advanced, which is more advanced than the logarithmic. That is a power law transformation, which is the coefficient will be multiplied with the original image with the gamma. So the with the power of the gamma, so which is give you the, which will correct the gamma corrections, so that again the whatever the we have got in the logarithmic images now, which will improve our images quality, so that the we can easily diagnose the images. And this is what is that, see, we can use power law transformation with that same image MRI. We can here the some parts, see some parts we are not able to identify, correct? So these small subjects we can't able to gather over in a logarithmic. So but when you are applying this power law transformation, we can able to get this. So all these particles, no, these are all we can able to get it clearly. And piecewise linear. Okay, next method is contrast stretching, gray level slicing, and bit plane slicing. So this will also useful for the enhancement of the image. So why we are going for the enhancement, in the sense before going for any processing, any identification of the diseases, we have to go for the enhancement of the images, then only we can able to do any corrections of the images. So low contrast images due to the poor illumination or due to the wrong setting of the aperture. Sometimes our lenses, everything we can't say which will be in terms of the correct. Okay, so that a low contrast image due to the poor illumination or due to the wrong setting of the aperture. The idea behind the contrast stretching is to increase the contrast of the images by making the dark portion darker and the bright portion brighter. so that the contrast stretching transformation increases the dynamic range of the modified images. Extreme contrast stretching yield thresholds. This is what is a contrast stretching. For this is a image contrast, low contrast and the optimal, and this is the high contrast, so that we can able to see the image clearly. And gray slicing, which is equivalent to the band pass filtering. And with this gray level slicing, we have a with background and without background. If you want to go for the with background, we have to use this mask, that is resultant. uh, See, this is a image pixels. With that image pixels, when you are applying these values, which is going to give that mask, that is s is equal to 7, which is going to transfer wherever we have the value of 7, that is the value of the lower value is going to replace into that is r is lies between r1 and r2, which is going to take it in terms of the 7. Okay, that's what. See, which is the values will be, this is the image, original image pixels. The value is which is lies between 2 and r1 and r2 we can take it in terms of the 2 and 4. So which is the lies between 2 and 4 will be replaced by, which is given in the red color. See, which is replaced by 7. And others will be as such original image, which is we are going to take it. Other values will be 0 and 1, whatever maybe. That is going to take it in terms of the as such the original image. With that is what, that is actually with background. And next one is the without background. For this without background, you can see this other than this red we are going to make in terms of the 0. That is what is a without background. So simply we are making into other. See, listen, with background, with the background we can see our images will be like looking like this. And without background we will be getting the pixels like this, which is we are making into a others and all 0. The rather than this values, other values we are making. So with and without background we are combining. When we combine, we'll be getting the planes. So so that we can easily make into your slices, and we can use for your uh, what to say, slicing the pixels. So that when you are slicing the pixels, this is the original plane, original image. Okay, when you are slicing it, so we'll be getting the image is accurate, the image particular parts what we are needed, no, that will be we can take in terms of this. See, we can take it into this is the first bit plane slicing, and second and third, fourth, fifth, sixth, and seventh, and the eighth image bit plane. So that when you're doing the slicing, we can able to get the images in a proper way. And when you are going for the brain tumor or brain tumor aid detection on the low contrast medical images. See, low, the image contrast is low means we have to increase the contrast. At the time, what we have to do in the sense, we have to take in terms of the input image. The image will be converted into a gray image, and finally we have to do the next, we have to do the enhancement. Next, a noise suppression has to be do. And this sometimes all the noises will be there in that images. For that only we have to use filters, whatever this required filter, no, median filter, mean filter, Gaussian filter, whichever suits for our images, we have to select that, and we have to do the filtering. And heads map generation has to be do, that is clustering of the clustering formation, whatever the fuzzy C mean clustering, or else fuzzy clustering, everything we can do. And the edge detection, with that we can use the edge detection. We can use a canny and sopel private through, but whatever the log edge detection we can do, and we'll be getting in terms of the proper image. This is what is the original image, and second one is the enhanced image. This is what is the procedure for the enhancement. We are in enhancement, we are reducing the noise also. When you are reducing the noise, some other unwanted things will be moving it. In forthcoming slides you will come to know what is, why we are doing all these parts. Okay, and sometimes we need in terms of the histogram stretching. Histogram in the sense, these are all with the pixels. We can, when you adjust the pixels, we will be getting the contrast, and image quality also will get improved. So image equalization technique is one of the main technique in histogram stretching. Yeah, when you are going for the image histogram, see, this is the image histogram processing. The image quality will be the pixels, nearby pixels, that values we, when we adjust, what will happen, this pixels image, original image will be enhanced. And next is a color histogram. So this is a cervical image. The women's reproductive system is one of the women reproductive system. This is the image of the cervix. Okay, and with that, when we extract, because when we see this image, this is not a original image, this is actually cancer image. Okay, these two are the cancer image. So to identify the cancer lesion, we have to see the image histogram and we have to adjust the colors. But by adjusting the colors, we can identify the, we can diagnose the disease. Okay, neighborhood processing, and we are using the smoothing filter and sharpening filter. Next, we'll be moving on to the frequency domain. In the frequency domain, actually, which is, I already told you, in a space defined by the value of the Fourier transform will be taken it, and which will be filtering, and frequency domain is actually straightforward. It consists of the following steps. Frequency domain will be having the following steps, which is multiply the input by -1 x plus y to center the transform, and compute the f of u comma v, the DFT of the image, and multiply f of u comma v by filter function h of u comma v. Compute the inverse. I already told you we have to take the Fourier transform and then we have to take the inverse. So that compute the inverse DFT of the above results. That's f of u comma v and h of u comma v. When you are multiplying, that will be taken in terms of the inverse DFT, and that result will be a real part of the results, and that will be multiply the above result by -1 into x plus y. So you will be getting the image, the enhanced image. So see, this is a frequency domain. We have to original image we have to take. Original images f of x comma y, that will be given in a pre-processing, and a Fourier transform will be taken it. Next, filtering the function, and inverse Fourier transform, and next, post processing. This is what is the steps involved in a frequency domain. That is what the previously what we are seeing, the steps, no, the same thing which is given in terms of the diagrammatic representation. Original image will be taken it, that has to be done with the pre-processing and Fourier transforming, and we have to apply the filtering functions. After filtering function, we have to take the inverse Fourier transform, and finally we have to take the post processing, and we'll be getting into of the g of x comma y, that is in enhanced image. Okay, this is for the smoothening and edge detection. Smoothening, we can use the low pass filtering, because in a Fourier transform, in a frequency domain, we are using the filtering function. So we can use for the smoothening the image, in the sense we can use a low pass filter. And for this, we have to take only edges, in the sense edges we have to take a clear picture, in the sense we have to go for the high pass filter. And when you're going for the filtering, all these hints has to be taken over there. And we'll move on to the color image enhancement. Here, when you are going for the color image processing, main part is RGB and lab color space, CAE color space, YH color space. The color space is taking a vital place over there. Okay, in that RGB lab color space transform with the some algorithms are there, so that we have to apply with the wavelets transforms, and we'll be getting in terms of the particular transformation. Okay, RGB in the sense red and green blue, like that. And L lab is also one of the color space we have. We'll come to know what are all that. And YH is also another color space, that is Young Helmholtz transformation and non-linear extrapolation algorithm. Yeah, when you're going for this, uh, any images for that, we should know the computer vision. For that, first we are taking as a input image. Input image is acquisition, that is you are taking the image, and next we are doing the pre-processing, and some finally we are doing the feature extraction. What are all the features we have to train the system, no, for that feature extraction. Next classification, finally post processing, and next final output we are going to get it. This is a computer vision. We'll see what is that. I'll be taking the example for that cervical image. This is a cervix image. This is a raw image. When you see this, these two are the speculums. I'll explain you. You'll be getting some idea of why we need this pre-processing everything, and how this will be useful for the doctors, and how it will make you as an entrepreneur. See, this is a speculum. To view the cervix, they will be inserting the speculum. When they are inserting this speculum, which is actually in a they will be pour some water to clean the cervix and everything they will be doing. So at that time it will be in terms of the wet, correct? So and that wet will be there, and due to this silver, that is silver speculum, it will be, you will be getting some glare. Okay, that glare you will be getting as a reflection, because without the light we can't able to see. The light will be focused on that particular part of the image, so that you are going to get the reflection on the particular image. This is actually a cervix, and this is not a lesion, or this is not a affected part. This is actually reflection due to this two speculums. Okay, speculum is a instrument due to the, because without that even if they wanted to do the eye operation, what they will do, they will open the eye with some instrument, is it? So that will make a glare to the eye, and that will be reflect in that images to rectify it. So what will happen here also, similarly we'll be having the a speculum, that reflections will be there in that cervix image. But by seeing radiologists, when they are seeing this, what will happen, this will be false diagnosing. This is not a cancer, but they will be imagining that this is the a cancer. So when we are making as our system, as a entrepreneur we are making as a system, what will be getting as a clear picture to the doctor, will be giving the clear picture to the radiologist to diagnose the image. We'll see how we are going to do that. So this is the original image. This is not a lesion part. This is a reflection. Due to the speculum, we'll be getting the reflection. This is called the speculum reflection. This has to be removed, because in every image definitely will be getting this reflection, because they will be pouring some acids, some liquids, they will be pouring to clean that part. When they are cleaning, that will be, that wetness will be there, because of that lightning, the you'll be getting some reflections that has to be removed. That is what, see here, the specular reflection has to be removed to diagnose it. Okay, for that we are going for the two processing. What are all the steps are going for the pre-processing? What we are going to do, we are going to remove the reflection. For that, ROI extraction, that is, and to remove the speculum reflection removal. Okay, this is a input image, and we are taking as a RGB to a lab color space, and GMM parameters we are going to, this is the procedure we are taking it, and clustering, some of the clustering we are taking it, denormalizing, and original RO image, and morphological operation, and extracted original image we are going to take. We'll see, this is what I'm going to do with the same image. When I applying these steps, okay, what my image is going to be. So given images will be taken into a RGB color space. When you see this image, this is the original image, this is the RGB image. So what I'm going to take, I'm going to take it in terms of the labs color space, that is lightning, level of the lightning, and the A represents the red or green, and the B denotes the yellowness or blueness. So L is the lightness, and the A is the red or green, and B denotes the yellow. So in my image, the major parts will be the red. Okay, so I'm going to take only the L in a, that's what I've selected the labs color space, because in my image I'll be having the red, most of the places having the red space. So I'm going to select the A color space, LAB's color space. Okay, and in lab color space, this is what is a conversion of the labs color RGB to the labs color space. This is what is the equation. Okay, I'm applying that, because why I'm selecting the A channel, that is LAB, in the sense L is one channel, A is another channel, B is one channel. Like RGB means red, green, and then RGB blue. So like that, LAB, luminous and red and green, and then yellowness. So I'm going to take only the A channel from that RGB image. I'm going to take the A channel, with that A channel, because my major part of the images carries a reddish in color. So that regardless of the lesion or whatever it may be, so major part will be covers with the red in colors. So that I'm selecting the lab color space. Yeah, when I'm converting this RGB into a labs color space, I'll be getting like this. See, L G channel will be converted into like RGB, entire RGB channel will be converted into L channel, A channel, B channel. We can take it into separately, and that in all these channel, I'm going to take this A channel separately. I'm going to process with that. I'm taking the channel and processing it. I'm taking equally distance. I'm applying some algorithms, so I'll be getting like this. Okay, and I'm applying the clustering with that normalization, I'm applying it, and filtering everything, I'm applying it. And here, this is the other parts will be taken, the speculum and all I've removed. Okay, and morphological image. See, previously our the steel things and all, they know that I've taken. Now how to remove the this, I've not removed anything. I've taken every other parts. I've taken my A channel, with that I've given that another, whatever the parts it is not required for me, no, that I've eliminated. And next, I'm for the speculum reflection, again I'm going to take a HSI, because here why I'm taking is a HSI means this illuminations will be high. That particular part I have to take. For that, I'm going for the HSI color space for the speculum reflection. The reflection I'm going to remove. For that only, HS hue, saturation, and intensity. So intensity have to change. For that, this is a formula for that. I'm giving a thresholding value. See, the from this I channel, HSI la I channel and S channel. With that channel, I've removed my reflections. See, I'm getting like this. Now this is what is the original image. That is not original image. The previously what we have seen is the original image, but after pre-processing it, I can see. But doctor can't see this in a, because they are seeing this in a colposcopy. They'll be, what they'll be doing, no, they'll be tilting that machine, and they will be, it will be painful for the patient also if they are changing the position of the machines, to see the lesion or not. The reflection, if once if we are getting the reflection, what we'll do, even in any vessels if it reflects means what we'll do, we'll be moving. If it reflects in on our face means what we'll be doing, we'll be moving and we'll be changing that reflection. So same way, what the doctor is changing the means, after fixing that speculum machines everything, they'll be tilting, they will be moving. What will happen, the patient will get more pain, because it is a very tough to insert that speculum everything. After inserted, they will be tilting and they will be moving, means patients will be getting more pain. So when we are going for this automatic processing, it will be useful for the doctors immediately. Once if they take the images, automatically you will be getting the images after pre-processing. After taking the images, pre-processing will be getting it. After that, we can see, we can give the diagnostic report that the patient is not having any cancerous lesion. See, this is what is a, even in a pre-processing itself we are getting this much clear. We are not doing anything, only the pre-processing we did. First stage of our processing or image processing is a pre-processing. Even that itself we are diagnosed, this is not a cancerous part. This is a original image, and this is a RO image, and this is a SR removed image. Okay, from this we can even pre-processing, we can easily identify, we can easily diagnose the a patient, because this patient is not having the cancer. And after this YH transformation and non we have already told, I have already told you about lab color spacing, because whatever my image carries, my if my image carries, if my image carries red color is dominated, in the sense how to take the lab color space, a color space. Yellow means I can have to take lab color space. And if the intensity wise I have to take, means I have to go for the HSI color space. And YH transformation and non-linear exploration algorithm, which is high frequency and low frequency components, and with the intensity means how to go for the YH transformation. This is what a enhancement, total enhancement algorithm with the original image and that intensity number matrix and high frequency component, low frequency component we have to separate. With that we have to compare low frequency, low pass filtering when you are applying, and after that high pass filtering, low frequency component will be taking it. With that we are comparing it, and we'll be comparing with the inverse YH transformation and giving it. And color space transformation, RGB, IHS, that is HSI only, they'll be naming as a intensity hue saturation. And with that conversion, this is a image, okay, original image, and in that also some reflections will be removed and lesions will be taken. Color image enhancement for the endoscopic images. See here also the reflections has to be, the reflection, some reflections will be there that has to be removed. Here without removing they will be taking it, and finally they will be diagnosing it. See all this, when you are applying this, all this color processing and color spaces, we can easily diagnose the images. And we'll see about the underwater. Even for this underwater images also, not even the medical image, I'm talking about the other image also. If you are processing it, we'll be getting the clear the sea image, and we'll be getting in terms of the clear images. Okay, with this the point processing method are basically used for the contrast enhancement, and the histogram equalization is not commonly used as a consumer electronic like television, digital camera, so which is adaptive technique used. Minimum mean brightness error dynamic histogram equalization preserves the brightness as well as improves the PSNR. And these are all the references we can go for this. When you are doing all these images, we are helping the radiologist to make up, because nowadays mainly what I have dealt with the cancerous patients, so they will be making in terms of they are going for the second opinion and third opinion like that. Once when you are adapting with this is a very good we have, there is no, these techniques will be combined with the colposcopy. With the, if it is for example I'm telling about the cervical images, these images will be all feeded with this colposcopic images, in the sense whatever they are getting in the colposcopic, they have to get in terms of the software, and they have to make a processing. Finally they'll be going to get the original image pre-processed, and final images they are going to get. With that everyone can make their ideas and their techniques. With that they can become the entrepreneur. Thank you. Is it, because all these will be helpful for the gynecologist for performing their USG, neurologist are doing their image again and again, they're asking to take the MRI and everything. No, instead of that they can go for this pre-processing everything. If they are going for that means definitely the diagnosing of the images will be identified. These are all the references, and these are all the references followed. Thank you. Thank you.
Participants, now you can unmute yourself and clarify your doubts. You can even post your doubts on the comment section below.
Finally, as an appreciation to Mrs. Dr. P.S. Ramaprabha for the time and valuable input she has shared with us all today, I would like to offer the small memento as an effort of an appreciation.
Yeah, thank you.
Welcome. Participants, the feedback link has been provided in the comment section. Please do fill it. Ma'am, the doubt has been posted.
Where can we get the medical images? We can get our medical images in even in radiologist, with the radiologist, and cancer institute, national cancer institutes. We can get the medical images in the national cancer institute also, with the proper documentation. When you are going with the MCC, we are getting that images. Yeah. Now next question is Dr. M Prem Kumar. Ma'am, what are the research issues in medical imaging? So nowadays, this even in a cervical image is also the issues, and mainly in a cancer issues will be there. Highly, the cancer issues will be there in our lungs, and these are all the highly taking parts. See, sir, mainly next question is, so what tool is better for the image processing? That is, we can use a MATLAB tool is a main thing, sir.
Ma'am, there is another question also posted.
Uh,
Regarding epilepsy images, one of the participants have asked.
Participant asked. Okay, sir. Okay. Sir, that epilepsy images. Sir, in neurologist only. I don't have any idea about the epilepsy images, sir. Sorry. Actually, any official websites, actually, more websites are there. But when we go with this websites, we won't get the paper when we are going for the paper presenting and all. Publishing and all, will be getting the plagiarism problem. So there is no particular official website for this getting images, ma'am.
Ma'am, I have one question, ma'am.
Yes, sir.
Regarding the filters used for either image enhancement or image segmentation. So, any common filter which can be used for both the image enhancement and image segmentation, ma'am?
Yeah.
Any
Sir,
filter?
what filtering is used for this enhancement and segmentation? What filtering?
Anything, ma'am.
Yeah, sir. Actually, when we depending upon the images, we have to select the filtering, sir. Either low pass filter or band pass filter. We can use band pass filter, that will be coming under all the categories. So basically, band pass filter also we can go for better results. We can go for the band pass. Depending upon the image quality, we can go for, sir. Basically, image processing, we it is not decided that when we want the edges means we have to go for the high pass filter. So similarly, and for the depending upon the image category only, we have to select the filtering. We can't say this is a filter will be suits for this image, like that we can't able to say, sir. Basically, band pass filter will suit for all the images generally.
Okay, thank you, ma'am. Thank you,
In
ma'am.
the sense, basically, high pass only we have to go, sir. Like that we have to categorize.
Okay, ma'am. Thank you, ma'am. Thank you.
Okay. Uh, mm, medical images. So another question is posted by Ma'am Satyapriya is medical images. Uh, what any official website get the medical, even that for the medical images only I'm telling, ma'am. If you are going for the medical images, there is no particular websites. With the lots of websites are there, but when you are going for the publishing the paper in a journal, when you are publishing, what will happen, it will show the plagiarism reports. That images will show you the plagiarism reports. That's what when you're going, we have to get the data from any officials, any radiologist or any doctors. When you are approaching, they will be giving the ideas. Surely doctors will be giving the ideas. So we have to go with that, and we have to take the fresh image, and we are publishing the papers. You won't get any plagiarism report, which is easy. That's what I'm telling. There's no websites are there, but when you're using from that websites, all the images already used images, so you will be showing the plagiarism reports. For the cancer image, we can approach the any cancer institutes with the proper MCC, a medical council. We have to get the approval from the medical, if medical council, and we can get the data. For that, we have to pay some amount for the recognized ethical things and all. We have to compromise, and we have to go for that medical data.
So, participants, if there are any other questions, you can ask. Participants, please post the feedback.
I would like to call Priyadarshini to hand over a vote of thanks.
I extend a very hearty vote of thanks to the honorable delegate who blessed us with their presence and took out the time for your busy schedule. Also, I would like to extend a special thanks to Dr. P.S. Ramaprabha ma'am for inspiring us, ma'am. I also wish to express my gratitude to our chairman, directors, and principal for providing an encouragement and support. I am very grateful for giving us an opportunity to organize this event. I heartily congratulate all the participants for their active participation in this event, as no program can become successful with a single person. So I extend my big thanks to each and every person present here. Thank you for making this event successful with your contribution. Thank you, ma'am.
Thank you, ma'am. Thank you.
Selvarani ma'am, please post the feedback link in the session box, ma'am.
It's posted. Chat. Already
Chat
posted in the
box.
chat box there.
Okay, ma'am. Can you please once again post it?
Okay, sir.
Okay. Thank you. Thank you, ma'am. Thank you. Participants, if you have filled the feedback link, you can leave the meeting. So thank you very much.
You can join us by tomorrow morning 10 a.m. for the next session. மீட்டிங்குள்ளே வரேன். மேம் கேட்குதா? தேங்க்யூ மேம். ரமா மேம் தேங்க்யூ.
Okay, sir. Thank you, sir. Thank you, sir.
Ma'am, thank you, ma'am.
ஓகே சார். மித்ரேஷ் சென்ட் பண்ணிடலாம்.
எஸ் சார்.
ஒரே நிமிஷம் இரு மித்ரேஷ்.
ஓகே சார்.
ரிமூவ் பண்ணிடலாம். ஒருத்தவங்களாம் ரிமூவ் பண்ணிடலாம்ப்பா. வெயிட் பண்ணு, நான் சொன்னதுக்கப்புறம் அடுத்த ஸ்டெப் போ. ஓகே சரி ஓகே. மித்ரேஷ் ரிமூவ் பண்ணிட்டு ஸ்டாப் பண்ணிடுப்பா.
ஓகே சார்.
ஓகே தேங்க்யூ.